Hi everyone, it's Mr. H here. In this video I'm going to look at the math behind the Doppler effect. In the description you can see a video about 3 minutes long that goes into the detail about what the Doppler effect is. And then we're going to now investigate how the math actually works with this. Before we do that, let's just quickly be reminded of what it actually sounds like. As something's coming towards you, the sound waves are compressed, therefore you hear a higher frequency. And as they go past you, the sound waves are stretched out, therefore you hear a lower frequency. Let's see if we hear that from these race cars.
Check here with Giafoni working him.
Right, you hear that, right? High frequencies is coming towards you, and lower frequency as it passes you. So those are going to be our first blanks, but let's just read through what this says first. Many different objects emit waves at a particular frequency. Sound waves, for example, are emitted by a horn in a car at a particular frequency, or in the case of the cars we just saw, the engines. If the car is not moving, we can see clearly that the same frequency of waves are emitted out from the car. The car is the source that the sound is coming from. Now, if the car is moving forward, it still emits waves at the same frequency, but due to the motion, the frequency that's observed, or the observed frequency, is higher when the car is moving towards you. The observed frequency is higher, then it sounds higher. And when it's moving away from you, the observed frequency is lower, and therefore it's going to sound lower. So here is a picture of the Doppler effect. We've seen this before. This idea that the compressing waves are in the beginning and the waves behind the vehicle are being stretched out. So not all moving sources of sound will generate a Doppler effect. The speed of the moving source must be a reasonable fraction of the speed of sound, at least about 10%. And the speed of sound in a normal 20-degree temperature, even around 0 degrees, is roughly 330 meters per second. So if we're somewhere around 30 meters per second, we're going to hear this Doppler effect. Notice as well that the person detecting the sound and/or the source, the car in this case, can be moving. If they are moving, we simply write the v source as the relative velocity between the source and the observer. So let's say, for example, I have a car right here, and it's moving towards another car right here. And let's suppose that the car on the left, it's a three-wheel car. The car on the left is the source. Okay, the sound is actually coming from that car. And so the observer would be over here on the right. And so let's say this was going at 10 meters per second, and this was traveling, the one, the source was moving at 20 meters per second. Well, then you would say that the relative velocity is 30 meters per second, because it's as though for the observer that the source is moving towards it at 30 meters per second. Likewise, if the observer was going the other direction, if it was going 10 meters per second in the same direction as the source, then it would be as though the source has a relative velocity of 10 meters per second. So we can simplify this to give us this equation here. That is, the frequency that we observe is equal to the speed of sound divided by the speed of sound plus the speed of the source times the frequency of the source. Now, depending on what textbook you're using, if you're using the Nelson Physics 11 textbook, this is not the equation that's in their textbook. And the reason that this is not the same equation is because there's some slight issues with the equation they've used in certain situations. In particular, their equation falls apart when the observer is moving. And so this will work regardless of whether or not the observer is moving. If the source is approaching an observer, then V source is negative. So in terms of just putting the observer at rest again, let's just draw this here quickly. So if a car is coming towards, and for the sake of physics, we're going to draw a box because we've done that with a lot of our objects. It's coming towards the observer, and this is the source. Then we will note that this is going to be a negative V source. However, if this object is moving away from the observer, then we would call this a positive V source. And so that's important to keep that in mind as we're doing this. Think about it this way. If something's getting further away from you, that's a positive difference. If something's coming closer to you, you're subtracting the distance to you. And so it's a negative distance. So let's go ahead and just define the variables in units quickly. They should be pretty relatively straightforward. The S of the observed is the frequency that is observed, and that's going to be in hertz. In the case of the F of the source, that's the frequency that the source emits. And that again is also in hertz, and we know that hertz is per seconds. And we know that the speed of sound is the speed of sound, just in words. That's in meters per second. And the speed of the source is the relative speed of the source compared to the observer, as I went over above. And that also is going to be in meters per second. So let's look at an example of how this can actually be calculated. A fire truck is moving toward an observer at 25 meters per second. The observer is moving toward the fire truck at 5 meters per second. If the frequency of the siren of the fire truck is 800 hertz, that means that from the fire truck's perspective, it's always going to emit that frequency. We want to calculate the frequency detected by the observer as the fire truck approaches and as the fire truck passes by, or just after it's passed. The temperature of the air causes the speed of sound to be 342 meters per second at this particular time. So let's write down some givens and calculate this. The first thing that people make a lot of mistakes on, and I recommend doing this, is to draw a quick picture of what's actually going on. Here's the truck. It's the source. So a lot of people make mistakes by just getting that first number, the speed of the source, wrong. Here's the observer. And we're told that the fire truck is moving toward the observer at 25 meters per second. This is going at 25 meters per second. We also know that the observer is moving at 5 meters per second towards the fire truck. So there we go. So what does that mean? Well, that means that the speed of the source is going to be 30 meters per second, because adding those two together, if they're coming towards each other, gives you 30. In other words, if the observer was standing still, it would appear like the fire truck's actually moving towards them at 30 meters per second. But because it's coming towards it, we also know that that means the source needs to be negative. So the other values that we know we need here are the speed of the sound. We know the speed of sound is 342 meters per second. And we need the frequency of the actually emitted object. So the frequency of the source is going to be 800 hertz. 800 hertz. So here we're trying to find the observed frequency. So there's my givens, there's my required. I can now do my analysis by writing out the equation. We know that the observed frequency is equal to the speed of sound divided by the speed of sound plus the speed of the source. We multiply all that by the frequency of the source. And so we put those values in. We get the speed of sound to be 342 meters per second. We knew that. That was given. We're dividing that by the speed of sound plus the negative 30 meters per second. And then I'm going to multiply that by the 800 hertz. And so some of you might say, well, can I cancel out the 342 and the 342? Absolutely not, because you need to remember that anytime you have a fraction, you need to add or subtract whatever's there first before you go dividing out common factors. So if you do this correctly, you should go 342 divided by 312, and that should give you a value of about 1.096. That whole fraction becomes 1.096 times 800, and you get 877 hertz. That is your observed frequency. I'll write a therefore statement at the end. Let's just look at the other situation now. Now the fire truck has passed by. So now the observer is over here. They're moving off at a speed of 5 meters per second. and the truck is over here moving at 25 meters per second. This is the source. And so everything is the same, except now your speed of the source, because they're moving away from each other, you're increasing the amount. Therefore, it's going to be a positive 30 meters per second. So everything else is going to be the same. So we take that same equation, and we can say the observed frequency is 342 meters per second. And we're dividing by 342 plus 30 meters per second now. We multiply that by 800 hertz, and we get a value of 735 hertz. Now, I noted over here that this whole fraction, this one right here, gave you a value of about 1.096. And this whole fraction right here gives you a value of about 0.919. And some people think that basically that you should, if you're up by 0.096 in the first case, should you not be down by 0.096 in the second case? You shouldn't be, right? And that just has to do with the fact that we're subtracting a value from the denominator. So it's actually giving us a difference. We've added 77 hertz in the first case, but we've only subtracted 65 hertz in the second case. So let's finish this off by writing a therefore statement. Therefore, the observed frequency is 877 hertz as the truck is coming towards, the fire truck is moving towards the observer. And 735 hertz as it is moving away. And there you go. That's how you calculate questions about the Doppler effect. So hopefully that equation is relatively straightforward. You may occasionally need to rearrange it for something, but in most cases we'll be solving for either the observed frequency or the frequency of the source. Finally, the last thing I just want to really briefly point out, and it was shown in the previous video that I've linked in this video's description, the Doppler effect in light. And so as noted, that energy can be passed through the atmosphere at different wavelengths as transverse waves, whereas sound is longitudinal waves. The wavelength determines the type of waves that are transmitted as shown on the right here. And so the Doppler effect doesn't only apply to sound waves, it applies to any waves that we see here. We see this in terms of our expanding universe with the visible light spectrum. And so that's a really cool application, and that's how we know the universe is actually expanding, and it's actually expanding now, we know, at an accelerating rate, which is actually quite a mystery to Big Bang theorists.